Right, good morning ladies and gentlemen. We're going to continue with chapter 8 in the textbook of Cengel and Ghajar on internal forced convection. And we did a lot of work in terms of, in general, looking at the temperature gradients and the velocity gradients. There's a question?
The sound is not good.
Oh my goodness, okay. I will just have to try to speak up, okay? Okay, unfortunately, I can't change it at the moment, right? Yeah, so we are. Yeah, so we were looking at the different temperature profiles and the velocity profiles in a tube, how it develops. So that is very important, and what is also important is the method of heating and or cooling. And there are two different methods, which are the constant wall temperature and the constant heat flux. And we did the theory of the two different methods, and I hope you could have seen how different the behaviors are of the two different methods. Quite different, and we have to use sort of different techniques in solving the problems. So what we're going to do today is paragraph 8.5, which is laminar flow in tubes. Then I'm also going to do an example, and then with the next lecture we're going to do turbulent flow. Right. So let's start with paragraph 8.5, laminar flow in tubes. Okay, laminar flow in tubes. Now the thing that is important with laminar flow in tubes is that this is the Nusselt number as a function of x. We did a lot about it. Then we know that we will have a behavior like that. This is the developing flow, and that is fully developed. So that's fully developed, and that is the developing part. Okay. Now, the method of heating or cooling is important. So if I have a problem with a constant heat flux, then the results would be maybe like that. And if it's a constant wall temperature, the results would be like that. And there will be quite a significant difference between the results for laminar flow. Okay. So we always have to remember that when we work with laminar flow problems. And it is always a judgment call that you need to make. So, for example, let's suppose you have a problem, a certain tube or a duct or whatever, and all the flow is fully developed up to that point. Okay. Okay. What you're then going to say is that for all practical purposes, I'm going to accept that the flow is fully developed, and I'm going to use the equations for fully developed flow. However, if I have the opposite, okay, if the flow is only fully developed maybe halfway through or 75% through, then you have to take into consideration the developing part, and you need to look for equations that can give you those results. They're not always available, unfortunately. Or in many cases, they are not available in your textbook, but they are available in literature. So there are lots of equations that you actually need to make provision for all the possibilities that you can get. Now, a very good example is the case of the constant heat flux, where we've got the Nusselt number of 4.36, and for the constant wall temperature, where it is 3.66. Okay. Now, this difference doesn't look like much, okay, but it is about 30% if you look at the values, and specifically in laminar flow, these values can actually be much higher if there's also secondary flow in the tube. So there can be quite large differences. Now, what you should also know that for laminar flow, it's not only the heat transfer that we are interested in, we are also normally interested in the pressure drops, because the pressure drops is what we pay for. We have to size a pump to ensure that we've got the flow through the tube or the heat exchanger. Now, for laminar flow, the friction factor is 64 divided by the Reynolds number. Do you agree? All of you? Nobody disagree with me? Then you're all wrong. Okay. Not really correct. You are correct, but not completely correct. Because that is only valid for a circular tube. That type of geometry. Okay. If, for example, it is a the geometry is a rectangle, like that, where that is A and that is B, then the friction factor would be 78.80 divided by the Reynolds number. And in this case, the AB, the ratio of this length to that length is 6. If the ratio is different, then the friction factor is different. Okay. If, for example, the tube is something like that, okay, and that is the angle theta, then the friction factor is 50.86 divided by the Reynolds number for the specific case where theta is 10 degrees. If theta is 20 degrees, then the friction factor is something different. Right. Now, where can you get this information? Well, it's all summarized in your textbook. In table 8.1, in the textbook of Cengel and Ghajar, you'll get more values than I've put up here on the board. Okay. Okay. Now, that is in general. Now, for the case, let's just summarize for a constant heat flux. For a constant heat flux case, that is H. Okay. In many cases, we will use the Nusselt number with a footnote H. Okay, then the Nusselt number for laminar flow would be equal to 4.36, and the Nusselt number for a constant wall temperature would be equal to 3.66. Again, that is true, but not completely true. That is only for the very special case of fully developed flow. So if the flow is developing, then that is not correct. Okay. So we also now need equations for developing flow. Okay, now in your textbook there is an equation which is called the Edwards equation. And this equation would then give the Nusselt number as 3.66 plus 0.065 multiplied by D divided by L, multiplied by Reynolds number, multiplied by Prandtl number, divided by 1 plus 0.04, multiplied by D divided by L, multiplied by Reynolds, multiplied by Prandtl, everything to the 2/3. And this is valid for a constant wall temperature. Okay, constant wall temperature. Very important is that this equation would now, if you go and plot it as function of x, or function of L, sorry. So if you use different values of L, you will see that if L becomes very large, okay, then this term would be very large, much larger than that one, and the result would go down to a Nusselt number of 3.66. So if it is very, very large, you'll get an answer of 3.66 for all practical purposes. Obviously, if it is now smaller, you're going to get something like that. But what is very handy of this equation is that this equation actually gives you the average, okay, from 0 to L. So this equation actually would give you that result there. Okay, the average. So if you've got a case where the flow is not fully developed, you can use the equation of Edwards, and that is then going to give you the average Nusselt number from 0 to L. Okay. Now something that has always been a problem in this textbook for students that really go and work through it in detail is after a while they come back and say, but where's the equation for a constant heat flux? And you'll see that equation is not there. Okay. Okay. Now what's the reason for that? The reason for that is that equation is extremely difficult to solve. The solution of it is pages and pages and pages of work. So in most undergraduate textbooks, they don't put it in. And if professors hate their students, then typically they will ask them to solve that problem. So it's not an easy one to solve. But Marilise and I managed actually to get a very simplified version of that equation, which is the following one. So for a constant wall temperature, a constant heat flux, there is an equation which is the equation of Shah, which has been published in a conference paper but not in an archival journal. And this equation gives then the Nusselt number for constant heat flux, and it is equal to, there are two equations, 1.953 multiplied by Reynolds-Prandtl multiplied by d of x to the half, or 4.364 plus 0.0722 multiplied by Reynolds multiplied by Prandtl d divided by x. And the equation says that you use the first equation if the Reynolds number multiplied by Prandtl multiplied by d divided by x is larger or equal to 33.3. Otherwise, you use the second equation if it is smaller than 33.3. So you can use that equation for a constant heat flux. However, take note, it is not the average value. Okay. So this equation is going to give you all the local values, and you will have to go and integrate it numerically or analytically to get the average Nusselt number for a constant heat flux case. Okay, you've got it. So laminar flow in tubes is very easy. You must always remember there are two parts, the developing part and the fully developed part. And you need equations for both. And in laminar flow cases, usually all the equations are for either constant heat flux or a constant wall temperature. So if you have a problem that you have to solve in industry, you first have to figure out, is it a constant heat flux problem or is it a constant wall temperature? Or in your application, which one of it is the closest to one of them? Okay, right. So let's do an example of flow of oil in a pipeline. Did you all write this equation down? I would recommend that you write it in pen there in your textbook, okay, not in your notes, because someday you're going to need it. It's not an easy equation to find. Okay, can I erase this part? Fine with everybody? Okay. Not? Okay, goodness. Okay, so it is Reynolds-Prandtl d divided by x larger than 33.3, and then the same term just for smaller than 33.3. Okay, so if that value is larger than 33.3, then you use this equation. If it is smaller, then you use that equation. Okay? Okay, so since you're still writing, let me start the problem then here. This is a problem of flow of oil in a pipeline. Okay. Now when we started with this chapter, you remember that when I discussed the Reynolds number, I've said that in most applications in industry, we've got turbulent flow. And the exceptions are where the viscosity of the fluid is very high or when the channel diameter is very small. So this is now a classical example of that. Okay, so we've got oil in a pipeline. Okay, and this pipeline, okay, so there's oil flowing through it. Okay, and the oil inlet temperature is 20 degrees Celsius. And it flows through an icy lake. Okay, so it's flowing through an icy lake, and this icy lake is 200 meters. Okay, so there's the surface, and it's an icy lake. And the diameter is 300 millimeters. And they ask us, determine the outlet temperature, TE. Okay. So this we are going to, of course, call the inlet temperature, TI. So we have to calculate the outlet temperature, and we have to calculate the heat transfer rate. Okay. And the pressure drop. The pressure drop. And the work required for the pump. The outlet temperature, the heat transfer rate, the pressure drop, and the work for the pump. So we're pumping oil 20 degrees Celsius through that pipe. And I think, if I'm not mistaken, that they also give us the velocity, which is 2 meters per second. I think so. We will check a little bit later. Yeah. Velocity 2 meters per second. Right. Now, we need to get the properties of oil. You agree? Because we will need the density, we will need the CP and the viscosity, etc. So for those of you who've got your textbooks here, please do me a favor and go and see if you can get the following value, because it's very important. So it's in table A13. Okay, so in table A13, and what I'm going to do is I'm going to do something silly now, because it is about this thing about the bulk temperature. What do you choose the bulk temperature to be? Okay, so the oil is going in at 20, you've got the icy lake, and therefore it would mean that in this case we have a surface temperature which is 0. Okay, it's not a constant heat flux problem. The surface of the tube all the way would be 0 degrees Celsius. Okay. Right, so if you go and look, okay, now what I'm going to do is I'm going to guess. I'm going to guess that my outlet temperature is minus 20 degrees Celsius. Okay. Why? Because I actually want to have a bulk temperature of plus 20 plus minus 20 divided by 2, which is 0 degrees Celsius. So just for the fun, let me choose a bulk temperature of 0 degrees Celsius and see what is going to happen. So my approach is now a little bit different than what is happening in the textbook. Right, so at 0 degrees Celsius, if we go and look in table A13, I hope you can get it, and then you will see there that the density is equal to 899 kilograms per cubic meter. The thermal conductivity is equal to 1.469 watts per meter Kelvin. The kinematic viscosity is equal to 4.242 multiplied by 10 to the minus 3 meters squared per second. The CP value is equal to 1797 joules per kilogram Kelvin. And the Prandtl number is equal to 46.636. You see that in your textbooks. You're all happy with it. Okay? Right, so the first thing we as engineers normally want to do is we want to know what the Reynolds number is, because if we know what the Reynolds number is, we can know if the flow is laminar or turbulent. So let's calculate the Reynolds number. The Reynolds number, which is equal to rho Vd divided by the viscosity. In this case, we've got the dynamic viscosity, so we can just write it as Vd divided by the kinematic viscosity. Okay. The velocity of the oil is 2 meters per second multiplied by the tube diameter, which is 0.3, divided by the kinematic viscosity, which is 4.242 multiplied by 10 to the minus 3, and that gives us a Reynolds number of 1414, which is quite as expected. So the flow is laminar. We've got laminar flow. The Reynolds number is smaller than 2,300. Okay. Let's see how long it is going to take for this flow to fully developed thermally. And it is equal to 0.05 multiplied by the Reynolds number, the Prandtl number multiplied by the diameter. And, okay, let's just put it in. 0.05 multiplied by the Reynolds is 1414, multiplied by the Prandtl, which is equal to 46.636, multiplied by the diameter, which is 0.3, and that gives us a length of 98.94 meters. So we are in trouble. So if we look at this problem, the Nusselt number as a function of x, the length of the pipe is 200 meters, okay? And 98 meters, almost 99 meters, the Nusselt number is going to do something like that, and only after that it's going to be a constant, okay? So it will only be fully developed after 99 meters. Question? Okay, just hold it, okay. Just hold it, okay. Right, that's fully developed, okay. I'm coming back to you, okay. Right, so it's fully developed, and what do you see? Almost half of the tube, it's not really, my scale wasn't very good here, but half of the flow will be developing and the other half will be fully developed. Okay. So we cannot now just say, well, it's a constant wall temperature and therefore the Nusselt number is 3.66. We cannot do that. We have to take the Edwards equation, we have to use the Edwards equation to take into consideration the flow that it is developing. And that equation will give us the average Nusselt number, which is very handy. So, the Edwards equation then is the Nusselt number is equal to 3.66 plus 0.065 multiplied by D divided by L multiplied by the Reynolds number and the Prandtl number divided by 1 plus 0.06 multiplied by D divided by L, Reynolds number, Prandtl number to the 2/3. Okay. And that would then give us a Nusselt number of 2.43. Okay. Are you happy? Does it make sense?
So I think it needs to be 0.04.
Where? Which equation?
1 plus 0.04.
Oh, all right. Sorry. Okay. 1 plus 0.4. Okay. Here you go. Okay. All happy with that? No, my goodness. How can that be? I'm giving you this. Okay. So that value should be 3.66. This equation is going to average something, so the result must be higher than 3.66, isn't it? So if you get something like that, then you've made an error. So always think about what you're trying to get. So the Nusselt number is 4.203. Okay, so it must be more than 3.66. Can't be less. Right? Now we've got the Nusselt number, now we can get the heat transfer coefficient. The heat transfer coefficient, Nusselt number is the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity. The Nusselt number we have solved as 4.203 is equal to the heat transfer coefficient multiplied by the tube diameter, which is 0.3, divided by the thermal conductivity of the oil, 0.1469. Therefore, we can solve the heat transfer coefficient as 2.058 watts per square meter degree Celsius. Now I just want to go and calculate some areas that we're going to use. And the areas that I would like to calculate is firstly the heat transfer surface. The heat transfer surface would be pi multiplied by the diameter multiplied by the length. So that is what is exposed to the icy water. That is pi multiplied by the diameter, 0.3 multiplied by the length, and that gives us 188.5 square meters. 188.5 square meters. The cross-sectional area is the flow through which the area through which the flow occurs. And that is equal to pi divided by 4d squared. I'm not going to put in the value now, but if you go and calculate it, it is equal to 0.07069 square meters. Okay, we're going to use it just now. Okay. Okay, so now with this type of problem, it always helps, just draw yourself a graph of all the temperatures. So what we have here is the icy water, which is at 0 degrees. The surface, sorry. Yeah, the icy water is at 0, and therefore the surface temperature of the wall should be 0 right through. You agree? The inlet temperature of the oil is 20. So there is 20. Okay. So it is going to decrease as it flows through the tube, isn't it? Okay. And the problem that we have here is a constant wall temperature case. Okay, now with a constant wall temperature case, if you look at the derivation of the few simple equations, we end up with the NTU method, e to the minus NTU. Okay? And that is the reason why I want to calculate the NTUs. Okay. So the NTU is equal to the heat transfer coefficient multiplied by the heat transfer surface divided by the mass flow rate and the CP. Okay, the heat transfer coefficient is equal to 2.058. The surface area is 188.5. The mass flow rate we have calculated somewhere, did we not? Okay, right. So we have to calculate the mass flow rate first. The mass flow rate is equal to rho multiplied by the area. Yeah, that is why we need the cross-sectional area. Cross-sectional area multiplied by the velocity. Okay, the density of the oil, I don't have it on the board anymore, but you can just put that in, multiplied by the area, multiplied by the velocity, and then you're going to calculate it as 125.6 kilograms per second. Okay, I forgot about that one, 125.6. Right, so the NTUs, number of transfer units, is the heat transfer coefficient, 2.05. The surface area, there it is, 188.5. The mass flow rate, 125.6. And the CP, which was on the board. And if you put in all the values, you get an NTU value of very, very low, 0.001699. What does it mean? It means that the heat transfer will be very ineffective. Not a lot of heat transfer is going to occur. Remember, if it is going to be 5, if that value is 5, then that outlet temperature of the oil would be about 0. But because it is far from 5, we know that that value is not going to drop a lot. So that is the advantage of what that NTU method is telling us. Right. Now, again, from the NTU method, we can now calculate the outlet temperature, and we've derived this equation previously. The outlet temperature is the surface temperature minus the surface temperature minus the inlet temperature, E to the minus NTUs. Okay. The surface temperature is 0, 0, 0, 0. 0 minus 0 minus the inlet temperature is 20. E to the minus NTUs minus 0.001699, and therefore the outlet temperature is going to be only 19.97 degrees Celsius. Okay. Okay. Which then means that if I go back to this graph, So I go back to the graph. Okay. And if I look at the oil, okay, so there is 20. So the oil is going to do something like that as it flows through the tube. Do you see? There's not going to be a large temperature drop. And if we now calculate the LMTD, the LMTD is, I just want to go back to this side again, and then I'm going to write it down on the other side. The LMTD is this temperature difference, that one is 19.97. This temperature difference minus this temperature difference divided by the ln of the two terms. So it's very, very simple. Okay. So it is equal to the temperature difference on the left-hand side is 20 minus 0. The temperature difference on the right-hand side is 19.97 divided 19.97. The ln of 20 divided by 19.97, and that is equal to 9.4 degrees Celsius. Okay? No, man. How can that be? LMTD 9.4. Look at the sketch. That's the advantage of making sketches while you work through it. If you go and calculate the LMTD, what is the LMTD? It is the effective temperature difference between those two streams. It's obviously 20, isn't it? You agree? It's 20 there, it's almost 20 there. Nothing happens. It's a delta T of 20. So if you do a calculation and you get a value like that, then you know your finger was the problem. Okay, so it is equal to 19.98. It's 20 degrees Celsius. Okay. Okay. So now we can calculate the heat transfer rate. It's equal to the heat transfer coefficient multiplied by the surface area multiplied by LMTD. Okay, the heat transfer coefficient, we've got the surface area and the LMTD. If we go and calculate it now, it is 7752 watts, or the engineering answer, 7.8 kilowatts. Right. Now, if I go back to where I've started, I've made an assumption, and that assumption was my outlet temperature is going to be minus 20. Therefore, my bulk temperature is minus 20 plus 20 divided by 2, 0. Obviously, that was not a good assumption. Do you agree? So, if you now redo it, now you need to realize, oh, that wasn't a good assumption, I need to redo it. So it therefore means that I'm going to say now my TE is almost 20, so my bulk temperature is 20. And at that bulk temperature, I'll have to go and get the properties again. Now look how it changed of oil, specifically from 0 to 20. You'll see a significant difference, and you will have to recalculate everything. Okay. You all happy with that? Right. Okay, now I'm happy to say that this was all wrong. Okay. Everything that I've done on the board now was wrong. Because there was a lesson that I want to learn you. And that is in the beginning, when we looked at all the properties, you all looked at it, I hope all of you looked at it, and you said you agree with me. Now, fortunately, there was one person who picked it up. Okay. And that is that be very careful. In many textbooks, you have to remember that an English textbook and a textbook which was printed in the UK or a textbook that was printed in the US, there are different nomenclatures. So this Prandtl number, just go and look at the Prandtl number again. So if you go and look at the Prandtl number, we have said the Prandtl number is equal to 46.6. It should have been 46,636. It's a big mistake. And many engineering accidents where lots of people were killed happened because of mistakes like this. Okay. So it is very important that you develop a feel for the fluids that you normally work with. You should know the density of water is about 1,000, the viscosity is about 1 multiplied by 10 to the minus 3. You should know that for air, about the density is this and the viscosity is that. You must try to develop a feeling for these values. Because while you do the calculations all the time, you must ask yourself, does it make sense and is it correct? So that is what we should have used, 46,000 and not 46. Okay. Now, if we now recognize this mistake and we want to redo the problem, there are another thing that we need to do, and that is we also need to look at the fact of the bulk temperature. Okay. So we have to now go and say, well, the bulk temperature is 20 degrees C. It's a much better assumption. And at 20 degrees C, now go and look in your textbooks for me again. What is the Prandtl number now? 20 degrees C, the Prandtl number is equal to 10,863. You agree? Okay. Now you need to redo this problem. And I want to ask you to go and do it at home because it is important. Because maybe I'm going to ask it in the test or the exam or something like that. Okay. But look how it changed the values. So I'm not going to write out everything in detail now, but I'm going to give you the most important values. So if you go and use this value now, the first thing is that the Reynolds number is going to change significantly. Not because of the Prandtl number, but just because of the fact that previously I've used a bulk temperature of 0, and now I go to a bulk temperature of 20. So it influenced the viscosity significantly. Okay, but it is still laminar flow. But look at this big difference. It takes, if we go and calculate LT, how long will it take before the flow is thermally fully developed? If we go and do this calculation now, it is 104 kilometers. 104 kilometers before the flow will be fully developed. Okay, so if we now look on a scale of 104 kilometers, okay, and we look at this problem of 200 meters, we are there. So all the flow is developing. There's nothing fully developed flow in this problem. So again, we will have to use that Edwards equation. And now look at what happens with the Nusselt number. The Nusselt number changes to 33.7, much higher than previously. Why? Because the flow is developing. It's not fully developed. So the average Nusselt number, according to the Edwards equation, is now going to change to 33.7. The heat transfer coefficient is going to change to 16.3. watts per square meter degree Celsius. The outlet temperature is not going to change a lot, 19.74. Still not going to drop a lot. The LMTD is going to be 19.87, so that's not changing a lot. The heat transfer rate, if you can calculate it, is going to be 61.1 kilowatts. The friction factor is going to be 64 divided by the Reynolds number, and that is going to be equal to 0.1006. Okay. And then we can calculate the pressure drop. The pressure drop is equal to the friction factor multiplied by L of D multiplied by rho V squared divided by 2. Again, all the values you can get from your calculations. And then the pressure drop is going to be 119 kilopascals. 119 kilopascals. And the pump work from fluid mechanics, it is the volume flow rate multiplied by the pressure drop, or you can write it as the mass flow rate multiplied by the pressure drop divided by the density. And if you can calculate it, it is 168 kilowatts that you will need to pump the oil for 200 meters at a velocity of 2 meters per second. Okay. Any more questions?
Just with that Nusselt number there, does that, when you say the average Nusselt number from the Edwards equation, does it include the fully developed region and the developed region?
Yes, it is a very nice equation. So even if it's going in the fully developed region, it will do the calculation correctly for you. So if the fully developed length is very, very long, the equation will go to 3.66 in any case. Okay. Right. No more questions? Right. The last part of this chapter is turbulent flow in tubes. Turbulent flow. Okay. Now, turbulent flow, there are, firstly, we need to know the friction factors. Now, the friction factor, there are many equations that you can use to get the friction factor. You've done them in fluid mechanics. Some of them are there in the textbook. But the Petukhov equation are quite accurate enough, and it is 0.790 multiplied by the lim of the Reynolds number minus 1.64 to the minus 2. And that is equation 8.65 in your textbook. So that's the Petukhov equation. So if the flow is turbulent, typically, definitely, Reynolds numbers larger than 10,000, maybe even 4,000 and higher, but between 4 and 10,000, you will not be sure. Okay, right. Now, the turbulent flow equations started about 70, 80 years ago, where people started doing experiments and developing equations. So all the equations that are presented to you in the textbook are from very old to relatively new. And the accuracies increased with time, improved with time. So some of the first equations, accuracies plus or minus 20 to 40%, and now with the last equations, Gnielinski equations, plus or minus 10%, but I'll say a little bit more when I get to that. Okay, so the first equation is known as the Chilton-Colburn equation. Okay, and that is the Nusselt number is equal to 0.125 multiplied by the friction factor multiplied by the Reynolds, multiplied by the Prandtl to the third. Equation 8.66 in your textbook. Okay, the Chilton-Colburn equation. But all of them, you will see the Nusselt number is a function of Reynolds number and Prandtl number, maybe friction factor and viscosity ratios. So all of them are like that. So they're all empirical equations. Then the next one is called the Colburn equation. The Colburn equation is the Nusselt number is equal to 0.23, Reynolds to the 0.8, Prandtl to the third, and the equation, there is a range of accuracies in the textbook of Prandtl numbers and Reynolds numbers in which it is valid, and then that is equation 8.67. So the Prandtl numbers should be between 0.7 and smaller than 160, and Reynolds numbers larger than 10,000. Okay. So then that equation would be valid. Okay. The next one is called the Dittus-Boelter equation. Dittus-Boelter means people that worked on the equation was Dittus and Boelter. Okay, so the Dittus-Boelter equation is actually a very nice equation to work with, especially if you're in a hurry. Nusselt number is equal to 0.23 multiplied by Reynolds to the 0.8, Prandtl to the n. Okay, and that is equation 8.68, and n is equal to 0.4 if the fluid is being heated, and n is equal to 0.3 if it is being cooled. Okay? Right. The next equation is called the Sieder and Tate equation. And that equation is the Nusselt number is equal to 0.027 multiplied by Reynolds to the 0.8, Prandtl to the third, and now the viscosity ratio, the viscosity bulk divided by the viscosity on the surface to the 0.14. And that is equation 8.69. And if you read the fine print, it says where there are large changes in properties. Now that is always something that is difficult for students to understand. Now they look at all these equations and they say, well, which one should I use? And when must I use this one? Okay. When you should use this one is you will have to look at the viscosity in the middle, the bulk viscosity, divided by the viscosity on the surface to the 0.14. Okay. So normally that would be close to 1. If that is the case, then the viscosity or the property changes are not significant. But if it is 0.5, then you know you will have to take it into consideration. Okay. Okay. Right. Now that is being followed by the Petukhov equation. Petukhov equation, which is equation 8.70. I'm not going to write it down. It is in your textbook. And then the last equation there is called the Gnielinski equation. Professor Gnielinski at Karlsruhe University, he developed this equation. Okay. And the Gnielinski equation is the Nusselt number is equal to the friction factor divided by 8 multiplied by the Reynolds minus 1000 divided by 1 plus 12.7 multiplied by the friction factor divided by 8 to the 0.8 Prandtl to the 2/3 minus 1. And if there's a writing error, don't worry about it. You can go and get the right equation in your textbook, which is equation 8.71. Okay. Now, if you go and look in your textbook and everywhere at these equations, they will not tell you how accurate they are. Okay. And the reason for that is that many of these equations were based on experiments that was done about 50 years ago. And 50 years ago, they didn't have the very good instrumentation that we have today. And for that reason, in our labs, we've been working on this over the past few years. And we have found that the Gnielinski equation, the accuracy is about plus or minus 10%. So it is within plus or minus 10%. But we've developed a new equation that I'm not going to write down here because we hope to publish it this year with an accuracy of plus or minus 3%. Okay, so we've developed one and we hope that it will work well. Okay, so if you want to have the equation, you can come and ask me later on for it. Right, so now the last thing that we have to also do in terms of the theory is that for all these equations is for a smooth tube. Okay. Now in industry, you know, we want to actually have heat transfer rates of much higher. And what has been done is that for many, many years, a new research field has been developed which is known as heat transfer enhancement. Heat transfer enhancement to enhance and to ensure that more heat transfer will occur. And it has been done by putting in typically fins on the inside. Okay. All different types that you can think of. Okay. Because now the surface area is more. Because the surface area is more heat transfer will occur. And you will even have cases where these fins, some of the tubes that we have at the moment is typically about 10 millimeters in diameter. And then they've got very, very small fins here. Typically a height of about 0.3 millimeters. Very, very small. But they are also spiraled on the inside, like the inside of a gun barrel. Okay, so what happens now is firstly there's more surface on the inside, but at the same time the bulk of the fluid is being rotated on the inside. And as you can imagine, that will also give you much more heat transfer. Now for all those cases where you have that, you'll need information. So you need graphs or you need empirical equations that can give you those values. And that is actually very, very important. So the cases where you've got a smooth tube type where you want heat transfer is actually very limited. Normally you would go to heat transfer enhancement type of tubes and make sure that more heat transfer can be enhanced like that. So ladies and gentlemen, that is all that I want to do in terms of the theory. Okay. The next lecture, I will also do another problem that addresses turbulent flow, of course. And as I've said, I will upload more videos of typical problems that covers this chapter on internal forced convection. Thank you very much. Okay.